Understood structure, tone, and meaning preserved. Only the wording change, and everything stays within YouTube's content guidelines. Here's the rewritten script. You're already gone. Not figuratively, not as a thought experiment. Measured against the timeline of the cosmos you inhabit, your whole existence, every recollection, every person you will ever cherish, every idea that will ever cross your mind, fills less time than a single heartbeat fills inside a human life. The cosmos is, at the very least, 13.8 billion years old. According to current physics, it will carry on existing for no fewer than 100 trillion years beyond this moment. Some projections stretch that figure to 10 to the power of 1,000 years, a number so immense that no name could ever do it justice. And you receive 80 years, 80 circuits of a mid-sized star on the outskirts of an unremarkable galaxy. That is your allotment. That is the opening you've been granted in a universe that will scarcely register when it shuts. Most people absorb this without blinking. They name it the human condition and carry on. But here's a question that ought to freeze you where you stand. Why does the physics of living insist on such a narrow opening? And does the universe genuinely require you to be brief? The answer turns on a number, so exact it rules out coincidence. And it may be the most unsettling thing physics has ever uncovered about your existence. Picture your grandmother's kitchen, or your grandfather's, or whoever filled that place in your life. The oldest face you can still summon clearly. You are seated at the table. It is a weekend morning. The light through the window carries that particular quality. Neither warm nor cold, simply honest. Something is simmering on the stove. There is an aroma you will never fully reproduce, no matter how many times you attempt it. And you look at that person, truly look, and you catch something you normally manage not to see. Their hands, the way the skin has altered, the particular landscape of a face that has been absorbing time for 7 or 8 decades. And somewhere behind your breastbone, a feeling surfaces that you have never quite found a word for. Not sorrow exactly. Something nearer to vertigo. Because in that instant you grasp something about time that no equation in physics has ever fully held. 80 years, fell from within, is both impossibly brief and somehow vast. That span can contain an entire cosmos of experience. First words, final words, the complete arc of loving another person. And yet, the light spilling through that kitchen window left the sun 8 minutes ago. That same sun has been burning for 4.5 billion years already, and it has not even reached middle age. You sense the imbalance without having any name for it. The cosmos beyond that window is old in a way that makes ancient civilizations look like this morning's headlines. The pyramids have stood for 4,500 years. The universe is 3 million times older than they are, and most of its existence still lies ahead. So why do the beings living inside it, the only ones we know capable of asking questions about it, receive such a vanishingly thin slice of that time? And here's the strange part. The physics indicates this is no accident. It may be the only answer available. Everyone asks them for the question, why do we leave so young? Philosophers have constructed entire careers around it. Religions have offered 100 different replies. It ranks among the oldest questions in human experience. But that is not the question that cracks everything open. The question no one poses, the one resting silently beneath all the rest, is this: why does biological life demand the particular time scale it runs on? And does that time scale share anything with the time scale of stars? Not why life is short, but why life is exactly this long, and whether that length was ever up for negotiation. Because here is what the physics genuinely reveals. Life as we know it, built on carbon, driven by DNA, metabolically active, cannot arise at just any moment in cosmic history. It demands very particular conditions. Specific elements must already exist. Specific stars must have already lived and died to manufacture those elements. Temperatures must fall within specific ranges. Planetary systems must have had the time to settle. And when you lay those conditions over the timeline of the cosmos, something quietly remarkable appears. The window in which life like ours is even possible does not stretch forever. It has boundaries. And the span of a human life rests inside that window in a way that does not look like pure chance. But here's the part that ought to raise a hair on your arm. The number that dictates how long you live, your 80 years, is linked through a chain of physics to the number that dictates how long stars live. And that chain passes through a constant tuned so finely that if it moved by 1 part in 10 to the power of 60, you would not exist at all. That constant carries a name. And what it says about your lifespan is either the most beautiful thing in physics or the most frightening. Perhaps both. The straightforward answer, the one biology textbooks offer, is that you live as long as your body can hold itself together against entropy. And evolution tuned that duration for reproductive success, not for longevity. That is true, and it is also, like most true things, only the surface. Here is the textbook account in full. Every cell in your body operates on controlled chemical reactions. Those reactions are fueled by molecules, ADP being the chief currency, that capture energy from food and release it in a form your biology can spend. Every one of those reactions produces waste. Metabolic byproducts build up, DNA copying mistakes pile on. Cellular repair systems, themselves expensive in energy, slowly fall behind the pace of the damage. Evolution never selects for immortality, because immortal organisms would crowd out their own descendants. A species that lived forever and kept reproducing would strip every available resource. Brief lives produce generational turnover, which produces genetic diversity, which produces adaptability. Your lifespan, in the textbook framing, is a feature of population dynamics, not a flaw in your personal design. On this account, 80 years is roughly how long a body running on this specific biochemistry, at this specific metabolic rate, inside this specific gravitational environment, can hold enough coherence to keep functioning. Mice get 2 years. Elephants get 70. Bowhead whales get 200. The pattern tracks loosely with size. Bigger animals run their metabolism more slowly, gather damage more slowly, live longer. You sit where you sit on that curve because of a combination of mass, metabolic rate, and evolved repair capacity. The textbook ends a chapter there. The answer comes out as you get 80 years because that is what your biology can maintain. And your biology was molded by evolutionary pressure, favoring reproduction over longevity. But this explanation, tidy and satisfying as it is, never poses the next question. Why does biology run on this physics at all? And what fixed the time scale of the physics itself? So the textbook tells you your 80 years is a product of biology, and biology, in turn, is a product of evolution, and that is where the explanation stops. But the cosmos does something far stranger. It binds your 80 years straight to the lifespan of stars, through a constant that has no business holding the value it holds. Here is the chain. Your body operates on carbon chemistry. Carbon was forged in stellar cores through a process known as the triple alpha reaction, 3 helium nuclei merging into a single carbon nucleus. That reaction succeeds because of an astonishing coincidence first spotted by the astronomer Fred Hoyle in 1953. Carbon possesses a resonance energy state at almost precisely the energy level this fusion needs to proceed efficiently. If that resonance were off by more than roughly 4%, carbon would never form in meaningful amounts. No carbon chemistry. No, but carbon only reaches the surfaces of planets once a star has died. A star like the sun burns for about 10 billion years. It then takes a few 100 million more years for planetary systems to form and settle around a resulting nebula. So carbon-based life cannot appear until at least 10 billion years after the Big Bang. That is a hard floor imposed by stellar physics. Now, here comes a number. The strength of a strong nuclear force, the force binding atomic nuclei together, sets how fast stars burn and how long they live. Were a few percent stronger, stars would exhaust their fuel in millions of years instead of billions. Were a few percent weaker, stars might fail to sustain fusion at all. The value it actually holds falls exactly in the band that yields stars with billion-year lifespans. That same force, at that same value, shapes the reactions unfolding inside your cell's mitochondria at an entirely different scale. The chemistry of life mirrors the physics of stars because both run on the same fundamental constants. Your 80 years is not arbitrary biology resting on indifferent physics. Your 80 years is a downstream consequence of constants tuned to yield stars that live long enough to make you possible. Imagine you could step outside of time, not outside the universe, only outside time. The entire history of the cosmos lies spread before you like a map. On the far left edge, the Big Bang, a point of infinite density. Then the first 3 minutes of nucleosynthesis, hydrogen and helium, and almost nothing else. You watch the earliest stars ignite, enormous, searing, burning fast. They live for millions of years rather than billions, and they perish in spectacular supernovae that seed the young universe with the first heavy elements. But no planets have formed around them yet. No chemistry yet complex enough for life. Generations of stars come and go. The universe is 2 billion years old now, then 3 billion. Elements are gathering in the interstellar medium. Carbon, oxygen, nitrogen, iron. But planetary systems remain violent. The bombardments never stop. No surface stays calm long enough. For billion years in, then 5, you watch a modest yellow star light up in an outer arm of a spiral galaxy. Planets take shape around it. The third one, your planet, slips into a stable orbit. Liquid water gathers. And then, somewhere between 3.5 and 4 billion years back by our count, something happens that still lacks any fully agreed explanation. Chemistry turns into biology. Now, watching from outside time, you can see the entire arc. 3.5 billion years of biological evolution arriving at a species that lives, on average, about 80 years. You watch generation after generation flicker in and out, brief lights in the dark. And from outside time, something catches your eye. Every one of those 80-year lives unfolds inside a universe that is still young by its own measure. At this moment, the universe has lived through less than 0.1% of its projected lifespan. You, and every human who has ever lived, exist inside the first fraction of a percent of cosmic history. You are not late to the cosmos. You are astonishingly early. That feeling you carry, that peculiar sense of being tiny and yet somehow first, is not an illusion. That is physics itself. If it turns out that humans rank among the earliest intelligent species the cosmos has produced, does that make existence feel more precious or more frightening? Because what follows, the physics of what the universe does after us, is something almost nobody has fully faced. And it transforms what 80 years means. That sensation you just had, standing outside time, watching yourself flicker inside the first fraction of a percent of cosmic history, is no metaphor. It is a consequence of something known as the stelliferous era. And once you understand it, the meaning of your 80 years changes entirely. Picture a candle that burns for exactly 1 hour. Now imagine that the first 30 seconds of that hour are the only 30 seconds in which reading by its light is possible. After that, the flame sinks to something too weak and too cold to be of use. You live inside those 30 seconds. For the rest of the hour, the remaining 59 and a half minutes, the candle keeps burning, but nothing reads by it. Your 80 years falls inside the reading window. The universe's future lies in a long, dark, cooling stretch that comes after. Astrophysicists split cosmic time into eras. The present era, the stelliferous era, from the Latin for star-bearing, stretches from roughly 10 to the power of 6 years after the Big Bang to about 10 to the power of 14 years. That upper limit comes to roughly 100 trillion years. Right now, we stand at roughly 1.38 times 10 to the power of 10 years, measured against the stelliferous era alone, not against total cosmic time. We are roughly 0.01% of the way through the age of star formation. Every star that will ever shine, every planet that will ever form around one, every chemical reaction that depends on starlight, all of it takes place inside this window. When the stelliferous era ends, the final stars burn out. What comes next is a degenerate era. White dwarfs cooling slowly across unimaginable timescales. Then comes the black hole era, then the dark era, an epoch so long and so empty that measuring it in years stops meaning anything. Here is what this reveals about reality. The universe runs on a metabolism of its own, like your body. It passes through a period of peak energy output, and that period is finite. The conditions that permit biology are not permanent fixtures of the cosmos. They are a phase, a season, and you happen to be alive inside that season. Your 80 years is not a small share of an infinite resource. It is a share of a finite window, one defined by stellar physics, atomic constants, and the pace at which the universe turns available energy into entropy. You are not brief inside an eternal universe. You are brief inside a universe that is itself, by cosmic standards, only briefly alive. That realization that the cosmos has its own metabolism, its own finite season of living, repeats at every scale of reality at once, from the smallest particle to the largest structure in existence. At the atomic scale, the constants that fix nuclear stability also fix the pace at which radioactive isotopes decay. Some isotopes carry half-lives of fractions of a second. Others carry half-lives longer than the age of the universe. The specific isotopes that make stable, long-lived chemistry possible, the kind able to build DNA and sustain across decades, exist only because a strong nuclear force rests at the exact value it holds. A universe with slightly different constants would yield chemistry either too volatile for memory or too inert to metabolize. Your 80 years depends on atomic stability across the scale of decades, and physics does not guarantee that stability. It is the outcome of a particular tuning. At the human scale, 80 years is just long enough to grow a mind capable of grasping its own brevity. That may not be coincidence. Some evolutionary biologists argue that the awareness of mortality, the capacity to model one's own non-existence, is cognitively tied to the same neural architecture that makes long-range planning, language, and symbolic thought possible. Your lifespan runs just long enough to develop the intelligence needed to question the lifespan. Whether that is beautiful or cruel depends on the day you ask. At the planetary scale, Earth holds roughly 1 to 2 billion years of habitability left before the sun's growing luminosity makes the surface too hot for liquid water. In geological terms, complex animal life on Earth covers only the most recent 600 million years of a 4.5 billion year story. You live in the chapter right before the ending, a chapter that is somehow also closer to the start of cosmic time than to its finish. At the cosmic scale, the universe is now deep in an accelerating expansion powered by dark energy. Galaxies past a certain distance are already pulling away from us faster than light, not by breaking relativity, but because space itself is stretching so fast that their light will never arrive. With every billion years, more of the observable universe slips beyond our cosmic horizon for good. The universe is not merely finite in time. In a meaningful sense, it is contracting, not in size, but in what remains reachable. Your 80 years lands at the moment of maximum cosmic richness. More of the cosmos is visible and reachable right now than will ever be again. The widest lens of all, the one that showed your 80 years falling at the peak of cosmic richness in the first fraction of a percent of stellar history, now zooms back to something you can hold in your hands. Most people picture their lifespan as a small quantity nested inside a large one. 80 years inside 13.8 billion. A rounding error, a footnote, but the physics points somewhere else. Somewhere that takes 3 statements to reach properly. First, the universe only became capable of producing life once it was about 10 billion years old. The elements had to be forged. Stars had to live and die. Chemistry had to grow more complex. No shortcut existed. If you squeeze cosmic history into a single calendar year, life would not show up until mid-September. Second, the era in which life is possible carries a hard expiration date. When the final stars burn out some 100 trillion years from now, the energy gradients that power metabolism will vanish at any scale compatible with biology. After that, the universe goes on, but nothing resembling you goes on with it. Third, you exist right now, not 10 billion years ago, while the elements were still being forged. Not 10 trillion years from now, when the last red dwarf will be fading. Right now, inside the window, in the slim band of cosmic time where the universe can produce something able to look back at itself and ask why it only receives 80 years. Here is a realization. Your 80 years is not a small slice of a vast eternity. Your 80 years is most of the window in which being you is physically possible at all. A human life, measured as a fraction of habitable cosmic time, is not brief by the standards of what biology demands and what physics permits. It is almost extravagantly long. The universe hands you the whole season, not a glimpse of it, the season itself. That recognition that you have been handed not a fragment, but essentially the entire available window, does not settle the question. It opens a harder one. If your 80 years is not cosmically briefed by the standard of what physics permits for life, then what exactly is a complaint? What is it you feel when you look at that kitchen table, at those aging hands, at the steam lifting off a cup that will go cold? It is not that you were given too little time. Maybe it is that you are standing inside a window whose edges you can see, and the view beyond those edges is something no human will ever witness. What comes after the stelliferous era is closed to us, closed to travel, closed to any technology we can foresee. The timescales involved are so enormous that they form a different category of existence altogether, not a longer life, but something outside the frame of life entirely. White dwarfs cooling across quadrillions of years. Black holes evaporating across spans that make the present age of the universe look like the first microsecond of a longer story. And the question that rises out of all of this is not, why do we leave? It is something harder. Does meaning depend on brevity? Or does brevity only feel meaningful because we have never known anything different? If you lived 1 trillion years, if physics somehow allowed it, would the first sunrise still matter? Would the smell of that kitchen? Or does the finiteness of your 80 years do something to experience that an endless span could never reproduce? Physics has no answer for that. No equation holds a relationship between duration and depth. But the question it leaves behind is this. The universe will remain here for a very long time after you. Is the fact that you were here first, inside the season, inside the richness, inside the light enough? Here is the image that remains with me. Right now, somewhere out in the universe, almost certainly, given what we know about how fast planets form and how common habitable zones are, there's a world where no one exists yet. A planet with liquid water, complex chemistry, and every physical prerequisite for life. Sitting in silence. No one asking questions. No one watching the light on the water. Only chemistry, patient and prepared, waiting another billion years for conditions to shift just enough. And here you are, already past that wait, already holding the very thing that world is still waiting to produce. The universe's reply to its own question, what can matter do when given enough time and the right constants? It is you, not you in particular, not your specific name or face, but the kind of thing you are, a creature built from stellar debris, running on atomic constants set 10 billion years before your birth, and capable of comprehending the settings. Your 80 years holds something the next 100 trillion years almost certainly will not. The first light, the early season, the moment when the universe is still making stars faster than it is losing them, still producing energy gradients steep enough to power thought, still near enough to its own beginning to remember, in some physical sense, what it was. You were always meant to be this brief. The physics required it. The same physics that made you possible also made you temporary, and made temporary feel like the only correct length. The universe hands you 80 years inside a trillion-year story, and somehow, against all mathematics, it is enough to ask why. If that question is still sitting with you, you already know where to find the next one.